Welcome back to ECE 320A. This is one class period prior to, bless you, prior to exam number 2. Homework number 5 is due today, judging from the tall stack of papers that have been turned in. But those can be turned in by 4 o'clock into my ECE mailbox. Question? It says what? No, that's when the deadline for it to disappear says. So I allow you to see that you missed it by an hour. The syllabus says 4 p.m. So the question was, why does it say 5? That's when that particular announcement ends. So according to the syllabus, all homeworks are due by 4. Obviously, if 10 minutes late, I'm not going to hopefully get too anxious about that, but we'll try to get it in by 4 o'clock. Thursday is your exam number 2. There is review material, old exams. We did a small review session yesterday. There are some YouTube videos now for calculators. If you haven't seen those, you might want to check those out. Those help you then do proper fraction expansion or partial fraction expansion on the proper part of that transfer function. Today what I want to do is quickly go over the process for exam number 2, and then we will look at performing this partial fraction expansion with complex roots using real numbers. Some of you have mentioned, wait a minute, I've seen it worked a different way. You'll get a consistent answer. It may not look exactly the same, but you are, hopefully, if you do the numbers properly or do the algebra properly, the answers are the same no matter how you find those partial fraction coefficients. Then we will get into new material relative to the exam with poles and zeros, final value theorem, initial value theorem, and then chapter 13, I believe, is here, dealing with transform networks. Can we simply go directly into the S domain or the frequency domain to analyze these circuits, and then all we have to do is rely on algebra. And we'll do algebra, except the algebra now involves complex numbers. But we still feel, I think, more comfortable doing algebra than we do solving differential equations, coupled differential equations. The process is consistent with exam number 1, except now you can have that same sheet that you had for exam 1 if you kept it, if you didn't burn it after the exam. If you kept that sheet, you can now add a second sheet to that with more material. You can bring a calculator and something to write with. What I might encourage you or suggest is that you include the following. It might be in your best interest. I'm assuming that you have tables 12.1 and 12.2 either burned into your memory or on a table somewhere. Those two are condensed into one page in the inside right front corner of your page of your textbook. If you want to simply photocopy those and make that one side of your second page of notes, that's fine. If you want to copy those down and create your own tables, that's fine also. But let's just keep to 2 pages of material. The other 2 equations that I'm suggesting you might want to have access to, you'll need to know how to use those, but this is when you have repeated roots. The top one, equation 83, is when your roots are real, and the bottom one is when you have complex roots. Oh, and I haven't quite shown you the complete result. Structurally, they are very close. Up top, on equation 83, k is a real number. Meaning if you now have a factor s plus 2 that's repeated 8 times, once you've found those 8 different k's, you can use each of those different 8 k's in the appropriate expression. Meaning if you now look at, oh, this one is 6 over s plus 4 to the 4th. Now you have r equal to 4, and you plug that into the appropriate location on the right-hand side to go into the time domain. You're now dividing by this 4 minus 1 factorial, or 3 factorial. And you're multiplying this decaying exponential by t to the 4 minus 1, or t cubed power. Even though that's going up as a cubic, your exponential will dominate as t gets big. It may initially bump up, but it will then decay as t gets larger. Likewise for the equation 84, if you have repeated complex roots, you will still need to find the k's. If it's repeated twice, you'll have 2 sets of k's. So you might have a K1 and a K1 star, and a K2 and a K2 star. And K, in this case, is complex. K has a magnitude and an angle, and the angle of that K, the book is labeling or identifying as theta, and the magnitude is what's indicated there as the bars around K. Questions on the process for exam number 2, and some suggestions for your notes that you are allowed to bring into class? Yes? I noticed that TI-89 is a partial fraction expansion, but we're still required to show all step-by-step work as if you didn't have that ability. What I am asking, and I think I suggested this in the lecture or in the review session yesterday, if you have a calculator that will provide, so the question was, how much work do we need to show? What I would like you to do is, if you had something like f of s, and it was, I'm going to do something somewhat easy. If you had something like that, then the calculator actually, if you simply say what? Expand, it will give you the 3 pieces in that partial fraction expansion. I would suggest that you say something like calc, or from calc, and then you would say whatever this is, a over s plus b over s plus 1 plus c over s plus 2, and you can write down directly what your calculator gives you for a, b, and c. I'm not calculating it here, but is that making any sense? And then you would then, if you're asked for the time domain expression for little f of t, then you better be able to inverse Laplace transform each of those 3 pieces back into the time domain. Does that answer your question? It does, and so the question was, doesn't that give you an unfair speed advantage if you have an 89 or higher? It does, but I'm going to try to write the exam so that it doesn't really matter. Okay? So the idea is, and what somebody suggested after the lecture was, well, if you know that this is the structure, maybe what you do is you say, okay, that's a plus b e to the minus t plus c e to the minus 2t u of t, and then you come back and fill in your ABC if you have more time, if you don't have the calculator, or even if you do. Is that making sense? I want you to know what you should be seeing or expecting from the material, not so much the algebra or the time involved in determining these numbers or numerical values. Question? We might have a run on the calculators. I don't know if you can check a calculator out or not, but that's an option. But I wouldn't come with an unfamiliar calculator to this exam expecting to really have an advantage because of a new calculator. If you don't know your calculator, that's probably less of an advantage than having your blue light special that you can now do divide and multiply with. You could, if you wanted, you could say from expand. The question was, can we write out the commands on the calculator? But I'm assuming that if you get this much information, well, if I want to know the commands, I'll come back and ask you, I guess. But yes, if you really want to, you could write down those commands if you have time as an outline. I thought I saw another hand on my right question. So the exam will cover homeworks 3, 4, and 5, topic-wise, and that then means the end of chapter 11 and pretty much all of chapter 12. Is that correct? So we have three-phase power, total power, complex power, and we have Laplace transforms and inverse Laplace transforms, and being able to apply those techniques in a circuit environment. Does that answer your question? There was another... I'm sorry? All right, I'll limit you to 5 calculators. So if you have... Just bring 2. So just bring 2 calculators if you feel more comfortable. So if you have your 4 function that you really like, and then you have maybe a brand new TI something, but you can't have a tablet or a laptop. It's just a calculator. Just a calculator. Wow. Yes. Yes, and you can also say, so the question was, or the comment was, we could also write this as a plus b e to the minus t plus c e to the minus 2t, t greater than or equal to 0. Those are equivalent expressions, and that's what I'm looking for, one or the other of those for your answer in this class. Question? So the question was, what about power meters? I will go ahead and individually create a problem for you, since this is your second question on power meters. It's essentially material like you've seen on the homework. If that section hasn't been covered or talked about anywhere, which we really haven't talked about the power meters section in chapter 11, then you don't need to worry about that for this exam. Other questions? You guys are not wanting new material. I know. You've been to school a few years. Where were we? Let's now look at the first topic on our list of topics, and that was to examine these complex roots in terms of partial fraction expansion when we have real numbers. I'm just going to walk through an example and hope that it makes sense. Suppose that you have 5s plus 2 in the numerator, and in the denominator somebody has generously given you the following structure: s plus 2 quantity squared plus 3 squared. Where are your roots? Or where are your poles? Because you have 2 sets of roots. You have numerator roots and denominator roots. We've been focusing so far on the denominator roots, which are the poles of our system or of our transform. In this case, where are the poles located? Yes, minus 2 plus and minus j3. If you substituted one one of those values for s, your denominator better vanish. If you replaced s with minus 2 plus j3, that better go away. And if you substituted s minus 2 minus j3, it also should go away. So those two values of s are your poles. But what you may have seen in an earlier class is you may have said, well, I don't know what this is, but I do know when I have complex poles at minus 2 plus and minus j3, I have damped sines or cosines. I don't know which one or what combination I might have, so it's possible that I could have both, and that's what you have to do in your expansion. You now say, well, let me just assume that I could have a little bit of each. Meaning, if I now wanted to say, what does the damped cosine expression look like? You would say, oh, the numerator contains an s piece. And if that's the cosine that's damped, what does the sine structure look like that's damped? We have omega, and then we'll just have another coefficient b. And now this, if we can find capital A and capital B, we can immediately write down a sum of damped sine and damped cosine, because that's exactly the structure, and that's why that s plus 2 is there. Maybe in some classes you've actually seen it written as a bar s plus, let's say, b bar for the numerator over just the 1. And they're equivalent, but I like to write it explicitly in the structure that I started with, which says the first one is the damped cosine directly, and the second one is the damped sine expression directly. And then I don't have to mess with a bar and b bar trying to split those up into sines and cosines. Are there questions on this? This is just another way, and now a and b are not going to be complex. They will be real numbers. I'll have so much of the damped cosine, and I'll have so much of the damped sine. What I would do then to determine that is I would say, well, let me go ahead and obtain a common denominator, or put them over the same denominator, which they already are. But now I can multiply this out, and I have as plus 2a plus 3b. And now I can equate coefficients. If I look at the coefficients that are multiplying s on both sides, in the original expression I had 5 times s, and in my partial fraction expansion I had a times s, and I immediately know that my cosine piece is weighted with a 5. And I can now find the b by simply looking at the constant coefficient, which on the left is 2, and on the right it's 2a plus 3b, but I already determined that a was 5. And b now becomes minus 8 over 3. Which allows me that now to conclude that f of t in the time domain is this 5 e to the minus, what is it? I simply go back and find where my poles were located, minus 2 plus and minus j3. The real part into the left half plane gives me the exponential decay piece, and that's now the minus 2. And the 3 gives me the damped frequency, omega sub d. And then I have the sine piece, and again, that's valid for non-negative time. Question? So this will be equipped. So the question was, is this the same? It's written differently, but this is an equivalent expression to what you found or would find if you found the k's, I'll use k's, that were complex. If we identified the distinct roots explicitly and looked at s plus 2 minus j3 and s plus 2 plus j3. And the way that you might show that is you could say, oh, well, this is a sine and a cosine of the same frequency. Those actually could be combined. And if I combine those, it will give me a shift, a phase shift in the cosine argument. Meaning if we wanted to combine these, I sort of like to just do it this way, where I have this chart, and here's my positive cosine axis. Whatever my coefficient is that precedes my cosine factor, I sketch it on the horizontal line. And the sine coefficient, if it's positive, I actually need to go down. If it's negative, I'm going up, in a sense. So my positive sine piece goes below on the vertical axis. In this case, I had, and this won't be, let's say, the same in terms of scaling, but let's say this is now the 5 piece, and my sine piece has a minus 8/3, which now brings me up here. This is now the minus 8/3 piece. And what I'm looking for now to make this look like more like what I maybe thought was happening before, I can identify this angle, and that angle is actually going to be a positive angle above the horizontal line, and my length, or the hypotenuse, so m is equal to this square root of 5 squared plus 8/3 squared, and theta is actually equal to the inverse cosine of 8/3 over 5. So I don't use the minus, but that's in the direction that I would take a minus value. Question? Why is the positive sign down? It's because of, if you go back to, so let me just write down the answer here. Does everybody understand what I did? Maybe not where it came from, but right now the 5 goes horizontal to the right, positive, and if I had a plus 2e to the minus 2t sine of 3t, the 2 would be below the horizontal line, and it would give me a negative angle. The reason for this change in sign, well, I said I wanted to write the answer down. F of t is now going to be some value, which actually ends up being 17/5, I believe, or 5, no, what was it? 17/3, 5.67 e to the minus 2t cosine of 3t plus 28.07 degrees. If you wanted to write this in terms of a sine, then you would write it relative to this positive sine axis, and that yellow highlight gives you the positive angle that you would write the sine piece in, if that makes any sense. And you would look at the length relative to that line. But let's just concentrate on using the horizontal. And why does it go up or down? It's all based on the trigonometric relationship. If you had r cosine of omega t plus theta, that's actually this r, and I'm going to write it in a funny way just because I want to And then this is minus r sine theta sine omega t. This minus sign is why that's the case. We have this mismatch between a positive angle inside the cosine, and in the expansion we have a minus piece. Meaning, if we actually, you may not have your answer written in the form that's given, but it might be something like alpha cosine omega t plus beta sine omega t. And now you want to convert that into a single sinusoid and the cosine structure. Then you say, oh, alpha is r cosine theta and beta is minus r sine theta. And once you do this, hopefully you can see that if you square both of these, you have alpha squared that's where your magnitude comes from. R is now the length or the hypotenuse of the right triangle formed by those two sides, and the angle theta, if you took the ratio of those two pieces, let's say that I now said, oh, I want beta over alpha, that's equal to minus r sine theta over r cosine of theta, or that's just minus tangent of theta. And now if you solve that for theta, you have that theta is the inverse tangent. Boy, my writing is terrible. Of this minus beta over alpha. Is that okay? So that's where the minus, but I just want you to feel comfortable. The other, if you did it the other way, which we've been talking about since half of you have these calculators that maybe want to play with complex numbers, the other way that you could do this as a check, you could say, well, this is s plus 2 squared plus 3 squared, but I'm used to doing this with the complex values, so this is going to be s plus 2 minus j3 plus k1 star s plus 2 plus j3. And it's critical that you find or you use the k1 associated with this particular factor. Where is the pole that associates itself with that highlighted term? So if you look at the value of s that causes that denominator to vanish, we're now over here at minus 2, and we're actually at plus j3, and the pole for this piece is that in the upper quadrant. And that's the one that you need to find the k1 for. K1 could have a negative angle, it could have a positive angle, and you just use whatever sign on that angle ends up coming out. But if we did that for this particular problem, hopefully if we did the algebra right, we would find that K1 is equal to 5/2 plus J 4/3. And this ends up being this 17/6 at an angle of inverse tangent of 8/15, which should have been the same angle that we had before. And this is actually half the distance that or length that we had before, because now f of t is 2 times 17 over 6 e to the minus 2t cosine of 3t plus that angle, which ends up being 28.07 degrees. And this becomes then this 17/3, which was the 5.67 that we had before. Hopefully that's okay. Question? Yes, so if you put the right signs on your real and imaginary part, depending on the brains in your calculator, it may give you the proper quadrant of the angle. A lot of times some calculators just give you an angle between plus or minus 90, and it may not give you the proper angle. So I always recommend that you sketch your piece and see what does this particular set of horizontal and vertical give me for an angle. Questions on that? So that's what you could do if you were more comfortable with the first procedure, which was to write or keep everything in terms of real coefficients or real numbers. Questions on that? You should get the same answer if you've done the algebra correctly. That's now exam 2 material. Let's now move into the new material, now that you're all going to check out on me, huh? Oh, it's not on the exam. So I'll take my glasses off and I can't see a face. And I won't hold you accountable. You're just a blur. But now let's talk about poles and zeros. This will be on the third exam and the final, so you might as well try to follow along. And we've already talked a lot about this. Suppose that somebody gives you the following transform, capital X of S, and now you're in a job interview and the guy gives you this on a napkin and he says, tell me about the circuit that produced this. And you go, brother, why did I interview with this company? So what could you tell the interviewee about a circuit that might have, well, we haven't, I guess, gotten there yet. But let's say this is now, yeah, I'm getting ahead of myself because I wanted to talk about transfer functions, and that's subsequent to this little lecture. But if this came from a circuit, what would the order of the circuit be if just this was describing the circuit? That's what I was trying to get at. Do you know what I'm asking? It's third order because that's the number of poles we have. And if we have a third order circuit, how many energy storage devices do we have? If we have a passive circuit, we have 3 energy storage devices. We could have a couple of inductors and a capacitor. We could have 3 capacitors. And this is what you could be telling the person that was interviewing you. You could say, oh, that might represent. And subsequently, we will talk about sketching the frequency response or the Bode plot associated with something like this. And then you could sketch that and you could say, oh, you've just given me a low-pass filter, or you've given me a band reject filter, or you've given me a high-pass filter. And you'll start to better understand what that means relative to the frequency response. In this particular case, this capital X of S can actually be factored on both the top and the bottom. The top is a second order, and it has 2 real factors. The denominator has and for discussion purposes, it might be convenient to write that the numerator polynomial, I will just call this expression capital N of S, and the denominator polynomial, I'll call it capital D of S. Now that I've done that, I can now talk about ways of making these polynomials zero. For example, values of S that actually cause the whole thing, the whole transform, capital X of S, to equal 0 are called, magically enough, zeros. That shouldn't take too much imagination to figure out why those are called zeros. Or you could say, well, instead of causing the whole transform to go to 0, we can talk about values of S that cause the numerator of X of S, which we actually called capital N of S, to equal 0, are called finite zeros. We're looking for finite values of S, bounded values of S that make little or capital N of S equals 0. And those are our zeros, or finite zeros. That's how they're defined. In our particular example, what would the zeros of that transform equal? If we go back to our example, the zeros are going to be at -1 and -3. And what we want to do is, you guessed it, go to the circus. Right? Here is our S-plane. This is our complex S-plane. This is a complex plane, meaning there are numbers, when plotted, would represent complex numbers. The imaginary, positive imaginary direction is up. The positive real direction is to the right. And we have now identified zeros, which we denote by open circles. And those are thumbtacks relative to our rubber sheet. So we now can think of this infinite extent rubber sheet that we will lay on top of this complex plane, and we may tack that rubber sheet down with thumbtacks. That's where zeros are located, and we may stick infinitely tall poles in regions of this complex plane that are associated with poles. And then the shape of that circus tent, especially if we walked along the imaginary axis, that's actually the magnitude of our frequency response. So we could look up, and if we were at the origin, that would be how that system responded at DC, at 0 frequency. If we walk up the imaginary axis and go to J1 and look up, now that's the frequency response's magnitude at a frequency of 1 radian per second. If we walked up to J2, it would be at a frequency of 2 radians per second. Question? So now the question was, what is a pole? Does it mean that we go crazy at a pole? And yes, that means that if we actually plugged in a value at that location, it would go unbounded, that particular transform. It would have an infinite magnitude, because what we're going to now say is we want values of S. Let's say values of S that cause capital X of S, this transform, to become infinite are called poles. And that's why these poles are infinitely long in length. They're representing the magnitude at that particular value of S. So something's going crazy. We did just hit a pole. Sorry. Or we could say values of S that cause the denominator of capital X of S, which we denoted as capital D of S, to equal 0. That's what we will refer to as finite poles. If we have a finite value of S, a bounded value of S, that forces the denominator or makes the denominator polynomial vanish, that's a pole. In our particular example, where were our poles? There's our transfer function, or our transform, capital X of S. We haven't yet said whether that's a signal or a system, and we'll get more into that later. This is now capital X of S. And the way that you've seen it so far is that probably represents a current or a voltage in the frequency domain. Where are our poles? We had a real pole at -5, and we had two complex poles that occurred in complex conjugate pairs because we started with real coefficients in our transfer function. And now if we go back to our sketch, we would have had a pole at -5, and we had a pole at -2 plus and minus J3, and -2 minus J3. And that's now our pole zero diagram for that transform. I could say, sketch the pole zero diagram for that particular transform, and you could draw these X's and O's. And somebody could say, oh, what's your basketball team doing in this play? X's and O's. Or we could play football, and we now have 11 X's and supposedly 11 zeros. So we have a lot. But you guys have calculators that will handle that. Questions on poles and zeros. But now what we want to be able to do is, if somebody says, oh, I want to know what happens when I'm marching along this imaginary axis, this is where the magic, whoops, I didn't want that to be blue. Now I'm going to have a hard time erasing that, so I won't. I wanted it to be a highlight. If I'm walking along that imaginary axis, that's going to give me the frequency response, behavior. And if somebody said, oh, what's this system going to do if this actually corresponded to a system when the frequency that you're interested in is maybe 5 radians per second, you would go to that dot location and find the magnitude and angle, and you could say, oh, this is how the system is responding at 5 radians per second. We'll get more into that later. But for now, what I want you to be able to visualize are these patterns of poles and zeros, and imagining these infinitely long poles coming out of the X's and thumbtacks on the circles and stretching a rubber sheet over the top of that configuration. Question? So now what is the real axis? If you think of what we have had before, the question was, I sort of understand this radians per second on the imaginary axis, but what's happening on the horizontal axis? If I said, oh, here is a system, or we've been dealing with signals, so let's just deal with a signal. Let's say that somebody gives you 4 over s plus 7. What would that look like in the time domain? What do we know? We know that this exponent is dimensionless. It needs to be dimensionless to make sense. And now we know t is a unit of time. Let's just call it seconds. So now this minus 7 is something per second. And radian is a dimensionless quantity. So we can say, oh, that's per second. And in the S-plane, we usually deal with radians per second. So this minus 7 is also a frequency. It actually gives us how fast we're collapsing as a time domain response, that minus 7. So we'll get a little bit more into that later, but you already have some of that information sort of built into what we've been doing. Meaning the horizontal line, you may not think of it as a frequency, but it is. And now every point in that complex plane, that's why we call it the frequency domain. We're playing with frequencies now in this complex S domain. And what they correspond to depends on where we're standing and what our system or signal is made up of in that complex plane. So now let's not get too hung up on interpreting this quite yet, but the question was, what's going on here? What's the frequency? Just think about where you are in a given location and remember how we were treating that. If we had a pole at, if we said something like s plus 4 minus j 8, and let's just say this is 3. If you had to inverse Laplace transform that, what would you have? It's e to the minus, or you could say it's really just this e to the st. Let me just go ahead and say what I was wanting to. This now we replace s, which is minus 4 plus j8 t. And I'm not including the conjugate piece. But even with this simple piece, hopefully you can see that we have an e to the minus 4t piece. That's how fast we decay. And we also have a complex exponential, e to the j8t. And if we put in the conjugate, that's going to be a sine or a cosine piece. So anytime when you see that j8, you go, oh, my frequency of oscillation is 8 radians per second. My decay rate is determined by the real part, which is e to the minus 4t. And we now have, in terms of a behavior, you could be thinking, and now I'm looking at the time domain response, I'm going to have some decay due to an envelope of decay due to this e to the minus 4t, and I'm going to have some oscillation due to the frequency. And now that you can see that that collapses, and if I slowed down my frequency of oscillation, what would happen? Now I would have something like this. And if I move closer to the real axis, my oscillation part gets bigger, but if I kept at the same distance into the left half plane of minus 4, the collapse rate remains the same. Or you could do just the opposite. You could keep the same oscillating frequency. Now it's just the decay rate might change if you move further or closer to the imaginary axis. And that's what I want you to start feeling or getting a feel for right now. Is that okay? Let's now move into the next topic, which was these theorems. And I know since we're engineers, that's what we really enjoy are these theorems. No, I just want to apply it. I don't want to know the theorem. But here are some very nice theorems that we can play with. Sometimes we are only interested in where we are starting in the initial value or the final value of this function of time, of the time function. And that's what then says, oh, let's now worry about determining the initial value, or let's worry about the final value. And the nice thing about these is we do not have to go we don't have to play the entire game. We can simply look at the transform and apply one of these theorems and see where we started or where we ended. We don't have to do the whole game and find the inverse Laplace transform and then look at what happens when t goes to 0 or when t goes to infinity. It's supposed to speed up the process. And we're an impatient bunch, so this is what we want. Let's look at the end first. Let's look at the final value theorem, because this is probably the one that you will be using more frequently. The final value theorem. First, we have a couple of conditions. If 1, x of t and its derivative if those two functions, if x of t and x prime of t are Laplace transformable, isn't there a toy named oh, I'm sorry, that's transformer, not Laplace transformable. Sorry. I thought you guys were playing with Laplace transforms, but it was transformers, wasn't it? Oh, okay. I thought maybe you'd already had all of this. What's it mean to be Laplace transformable? What in the world does that mean? It's well behaved. It's a physical signal. It exists. It's not e to the t squared. It's not blowing up faster than exponentially. So that's the first condition. We have nice properties on x and x prime. The second condition that we now want to look at this expression, capital X of s, scaled by s. And we do not want any of the poles of this resulting expression, we say, has no poles on the imaginary axis, on the j omega axis, or in the right half of the S-plane. And now you know what poles are and where they live. And if you have poles either living on the imaginary axis or in the right half plane, you can't apply this theorem. If that pole, if after you've hit capital X of S with S, so you've canceled one pole at the origin, that's the possibility of that S. If you can eliminate one of those poles at the origin, if it even exists, and there's nothing left pole-wise on the imaginary axis or in the right half plane, then you can apply this theorem. That's what this is saying. If you have these two conditions satisfied, then we have the theorem. The limit as t goes to infinity of x of t, that's the final value of the waveform. We can find that by simply letting s go to 0 of s capital X of s. Meaning that's going to be a lot easier than inverse Laplace transform. All we have to do is multiply by s and let s go to 0 and see what we get. If we get a number, then we know where we're headed in terms of a final value. Where did this come from? This is what we like, the proof. All right, so it's not going to take much. Let's just assume that x of s has a Laplace transform, capital X of s. If I now look at Laplace transforming the derivative, this is a review question for Thursday's exam. What's its Laplace transform? That's the time domain value of that waveform at 0 minus. So now let's use that information. We have s capital X of s minus x of 0 minus. That, by definition, is this integral from 0 minus to infinity of x prime of t. What is the definition of the Laplace transform? There's the function that we want to transform. Now what do we scale that by before we integrate? This decaying complex exponential, or this e to the minus st dt. That's now the definition of our Laplace transform. Let's now look at what we can do. Well, let's just keep this s capital X of s on the left and put the other piece on the right. And now the other piece on the right is this 0 minus to infinity, x prime of t, e to the minus st dt, plus x of 0 minus. And what I want to do, actually, is look at this now as s goes to 0. If that's the case, what happens in this integral? I'm integrating with respect to time. So that integral doesn't change, that part, as far as the limits. I'm integrating from t equals 0 minus up to t equal infinity. But inside, that s now in e to the minus s, if it goes to 0, what happens to that scaling piece, e to the minus st? It goes to 1. So now I have x prime of t. Well, maybe I should have done a different That's okay, I guess. And now what do I have? I still have that x of 0 minus. That didn't have an s term in it. But what's this integral of x prime dt? That's just the integral of dx, isn't it? So that's going to be x at the upper and lower limits, meaning I can now say that that's x at infinity minus x of 0 minus plus x of 0 minus, which is our x of infinity. Meaning, that's what we were looking to prove. We now have that the limit as t goes to infinity of x of t, which is this x of infinity, is equal to the limit as s goes to 0 of s, capital X of s. And that's what we were trying to show. Let's look at some examples of how this then can be applied. Suppose that we have the following. Suppose some output voltage, Laplace transform, is given as minus 4 over 2s squared plus 3s plus 1. We usually like to have our denominator or a monic denominator, don't we? What does that mean? Do you remember? Did I define that in here? What's it mean for a polynomial to be monic? M-O-N-I-C. The first coefficient is 1. And we can make that happen in this particular case by factoring out the 2. And we have s squared plus 3 halves s plus 1 half. So what? Well, what you can learn is that if you now have factors that are quadratic, all you really have to do is look at those two lower powers of s coefficients, the s0 coefficient and the s1 coefficient. As long as both of those are positive, you know that the roots are going to have a negative real part. And that's what you want. You want them to be in the left half plane. So just looking at this by inspection, these poles are in, and I'm going to abbreviate that as LHP. And that's because those coefficients were both present and positive. Okay, because they were both there and positive, then we can immediately conclude that they correspond to poles in the left half plane. And for this theorem, we don't have to identify those poles. We just need them not to be on the imaginary axis or in the right half plane. And we've now concluded that. Now we can figure out what the time domain behavior of this voltage is going to do as t marches off to infinity. We can now say that we're looking at the limit as s goes to 0 of s v naught of s. And what does that look like? We now need to multiply or scale this expression by s. If we do that, we now have minus 4s over 2s squared plus 3 halves s plus 1 half. What happens as s goes to 0? What happens upstairs? We can look at this, if we want, in two pieces, the limit upstairs and the limit downstairs. What happens upstairs? What happens downstairs? We plug s equal to 0 in, and we're left with a constant. In this case, it's 1, but we had 0 upstairs. So this is going to go to 0. And if you did the inverse Laplace transform, you have decaying exponentials, either real or complex, and your output voltage is going to go to 0. So that makes sense. What about another one? Suppose we say here is x of s, and it is 6s plus 1 over s squared plus 1.5s plus 0.4. If we look at these two, are those in a good place or not? They're both positive. So what we will refer to that actually is they have decaying exponentials. We'll call that a stable response. So those are stable poles or poles in the left half plane. And that's a good thing. Now what happens if we apply the final value theorem? We're looking at the limit as t goes to infinity of little x of t. That's equal to the limit as s goes to 0 of s capital X of s. That's now the limit as s goes to 0 of 6s plus 1 over, and now that s upstairs cancels the s downstairs. I'm not even going to write those two. And this is s squared plus 1.5s plus 0.4. What happens is s vanishes. Upstairs I get 6, and downstairs what do I get? Now I know my final value is 15, and I didn't have to do any kind of inverse Laplace transforming. I immediately know that I'm going to settle at a final value of x of t equal to 15 as time marches off to infinity. Another example. Suppose y of s is 1 over s minus 1. Do you now start to see where these poles are located when you just look at the factored form of the transform? Where is this pole? It's in the right. So if you inverse Laplace transformed this, what would little y of t look like? You just told me this looks like a pole in the right half plane, which should be starting to put alarm bells into action. What's y of t? E to the plus 1t. And what's that doing as t goes to infinity? It's not very well behaved, is it? It's going unbounded. So now if you build a system, and this system actually had a pole in the right half plane, you plug it in, and what's going to happen? You may start smelling something, right? It might start burning. And Josie might come running. There's the alarm bells. That's the fire bell, right? You might set off a fire bell with poles in the right half plane. Now, what if you made the mistake and you said, oh, I remember the final value theorem. What happens? Well, now you just start whistling. You go, oh yeah, this is fun. I'm going to do this. Let's see. Limit as t goes to infinity, y of t. Oh, let's see. Tharp said that was the limit as s goes to 0 of s, y of s. Oh, this is looking like it's going to work. Limit as s goes to 0 of s over s minus 1. What's that going to give me? Oh, good. This is well behaved. What happened? This violated one of those first constraints in our theorem, didn't it? This had a pole in the right half plane, so we can't apply the final value theorem. This is then the no-no. So you can't just assume for the final value theorem, if you get a number, that it's correct. You need to make sure and check the premises. And one of those premises was look at s, x of s, and make sure that the poles of that result are not on the imaginary axis or in the right half plane. In this case, we had a pole in the right half plane, which is going to send us off to Never Never Land in the actual result, and we think, oh, with the final value theorem, if we apply it incorrectly, that we are okay, and that we're not. All right, one more. Suppose that we have z of s equal to 2 over s squared plus 4. Now what? We have a quadratic, and what did we say? Oh, where you need to look for the coefficients. Oh, it's positive. How many coefficients do you have? You should have 2 besides the s squared. So you're missing your linear coefficient. You have 0s. And now where are these poles? They're at plus and minus j2, aren't they? So if this is a signal, z of t, if you now looked at this, z of t is actually the sine of 2t. And we've said, oh, let's start it at time u of t. Now, if we looked at the limit as t goes to infinity of z of t, what can we say? I'm going to find it. I'm going to find it. You're not going to see it, are you? It's never going to settle. You're watching t as it grows and grows, and now you're just oscillating. It's indeterminate. It doesn't reach a limit. It's on the imaginary, the poles are on the imaginary axis. It's just going to bang back and forth. At what frequency? So it's not going to work, is it? If you were in your la-la land again and just trying to get an answer, and you tried to apply the final value theorem, it's going to be a no-no again, isn't it? Because this is going to look like it's well behaved. It's going to 0, but the fact was your premise was incorrect to begin with. You need to make sure that you check that, make sure that the roots or the poles of s, x of s, are not on the imaginary axis or in the right half plane. If they are, you can't apply this. And now you see why you can't. You can have complex roots They just need to have real parts that position them into the left half plane. We'll pick up at that point a week from today. Thursday is the exam. Make sure and turn in your homework.